levels because it will have a segment list. Let's say if the segment list has many nodes inside, then we will have many levels in the stack. The active segment is the top level of the stack. On the other hand, SRv6 uses a new IPv6 extension header called the segment routing header or SRH. Segments are encoded as IPv6 addresses, and the entire list of the segment are encoded as an order list of IPv6 addresses in the segment routing header. The active segment is the IPv6 destination address. Along the way, I will mention about in SRMPLS how it will be, in SRv6 how it will be, but mainly today our focus will be on MPLS part. Okay, terminology time. Normally terminology time, you will need to memorize many things and will have a lot of question mark in the mind. Segment is an instruction. A node executes on an incoming packet. For example, to forward the packet according to the shortest path to the destination, or forward the packet through a specific interface, or deliver the packet to a given service or application. Here, to forward packet according to the shortest path to destination, this one is typically if the segment is a node. And then to forward packet through the specific interface, this is the situation where a segment is an interface connecting to the neighboring router, which we call an adjacency segment. And then for delivering the packet to a given service or application, this is the case that I said, to trigger a function at the destination router. The global segment is the segment that is supported by all SR capable routers in the SR domain, while a local segment is the segment that only supported by the router originating it. The segment identifier or SID, or we call Chit, is for identifying a segment. It is an MPLS label in SRMPLS and it is an IPv6 address in SRv6. The label value of Chit in SRMPLS can either be an absolute value or a calculated value based on a unique index. This one I will explain more later in the presentation, in which case we will use a unique index, in which case we will use an absolute value. SR policy, also known as segment list, is an order list of seeds encoding the order set of instructions to be applied to a packet as it traverses an SR domain. So basically, it is a list of segments, and then in MPLS case, it will be encoded as the label stack in MPLS. And for IPv6, it will be a list of IPv6 addresses in segment routing header of the IPv6 packet. The segment list can either be computed locally or provisioned by a remote system. When provisioned by a remote system, it can be provisioned using like netcon or a protocol called Path Computation Element Communication Protocol, PCEP. It is the protocol that can be used on the controller to signal the specific path to the head-end router. SR domain is a set of nodes participating in the source-based routing model. Still many terms. Okay. SR global block or sRGB is a set of local MPLS labels reserved for the global segment. In the case of IPv6, SR with IPv6, sRGB is the set of global SRv6 seeds in the SR domain. For SR local block or SRLB, is a set of local MPLS labels reserved for a local segment. In the case of SRv6, SRLB is the set of local IPv6 addresses reserved for local SRv6 seeds. And the active segment is the segment that is used by the receiving router to process the packet. Normally in SRMPLS, the active segment will be the top level of the MPLS level stack, and in SRv6, it will be the destination address of the IPv6 packet. Segment list depth refers to the number of segments in the segment list. So if you have 3 segments, then the depth is 3. When a packet comes into an SR node, it will perform one of these three operations. Actually, when we see here, it is very similar to MPLS. That's why there is a comparison here. For the segment routing, we use the term push, next, continue, while MPLS is push, pop, and swap. So for the push operation in segment routing, when implemented in MPLS data plan, it becomes the push operation of MPLS, while next is pop operation and continue is the swap operation. Push is an operation of inserting a segment at the top of the segment list. In SRMPLS, the router will push a new label to the label stack, and in SRv6, the router will set the first segment in the IPv6 segment routing header. Next is an operation of signaling completion of active segment and activate the next segment in the segment list. In SRMPLS, it is popping the top level of the stack, and in SRv6, the router will activate the next segment in the segment routing header by copying it to the destination address field of the IPv6 header. Continue is an operation of signaling that the current active segment is not yet complete and needs to remain active. In SRMPLS, the router will swap the top level. In SRv6, the router will do standard IPv6 forwarding based on the destination address. If it sounds complicated to you, actually it is simple. Push, normally we do this on the head end router. And then next, normally it is at the tail end router or maybe at the intermediate point that we need to change the segment. It arrives to a point that we need to change. Let's say we are saying that from PE1 to PE2, you need to go to P3 first. So when arrive to P3, the next operation will happen because P3 will pop the label and then it will continue to process the next segment. Continue means along the way to the destination of the label. The destination for in case of IPv6, it is the destination of the segment. Segment routing provides flexible support of distributed, centralized, or hybrid control plane options. A distributed control plane means the segments are allocated and distributed by routing protocol like ISIS, OSPF, or BGP. On the other hand, a centralized control plane refers to scenario where the segments are allocated and instantiated by an SR controller communicated with the router either through netcon, PCP, BGP, or other means. If, let's say, the controller does not speak any of this protocol, then maybe the controller can simply SSH into the router and configure the command. It is also possible. It doesn't have the restriction saying that the controller must speak these protocols. The hybrid option is a combination of distributed and centralized control planes. IGP segments are used for identifying information advertised by an IGP in the context of a prefix, topology, and algorithm. The advertisement of IGP segment is done via IGP extension for segment routing. There are two main categories for IGP segment: the IGP prefix and IGP adjacency segments. An IGP prefix segment, also known as a prefix seed, represents an IGP prefix. It can be an IGP anycast segment or anycast seed that represents an anycast prefix or an IGP node, or we call node seed, that it identifies specific router. An IGP adjacency segment, also known as adjacency seed, represents an IGP adjacency. In another word, it identifies a specific interface connecting to the neighboring router. We will dive into each type of seed in the coming slides. So basically, adjacency is for identifying the link, while prefix seed is for identifying either a node or an anycast destination. So for example, in segment routing, if you are saying that I want to go to PE2 through router P3, so this so-called router P3 is a node seed. You don't care how it will go to P3. maybe it will take the shortest path. You just want it to arrive to P3 with the shortest path. Then it will be a node seed. But maybe when arrive to P3, in this P3 might have multiple interface connect to the neighboring router. So in that case, if you want to say that in P3, you must use gigabit Ethernet 1 to go to the next hop, then it will be an adjacency seed. This is for specifying the instruction for a link. This is for specifying instruction for a node. A node seed is used for identifying a specific node in the network. They are globally significant by default. Node seeds are essentially instructions to forward a packet via the shortest ECMP aware IGP path to the destination node. Node seeds are advertised by the link state IGP like OSPF or ISIS. They need to be manually configured by the network operator on NMS. An Anycast seed is advertised by all the members of an Anycast set. All routers in the set advertise the same Anycast prefix and seed value. They are globally significant by default. And Anycast seed are essentially instruction to forward a packet through the shortest path to the topological closest member of the Anycast set. So it means if you have an Anycast set of 4 routers, so you just tell the router, say that the head-end router saying that you just forward the packet to any of these 4 routers. I don't care which one, the closest one you just forward it. Then this is an Anycast seed. Anycast seeds are advertised by the link state IGP like OSPF and ISIS. For adjacency seed, it is used for identifying one or more adjacency in specific node. The node typically allocates one adjacency seed for each of its adjacency. It may also allocate multiple adjacency seeds to the same adjacency or the same adjacency seed to multiple adjacency for the purpose of ECMP. Adjacency seeds are locally significant by default. They are installed only in the FIP of the originating router. This requires the adjacency seed to be preceded by the node seed of its node to allow the correct forwarding. For example, if you want to say to P3, say that you forward the packet through gigabit Ethernet 1 to the next router, then at least you will need to give the instruction for the packet to arrive to P3 first. Otherwise, other router will not know gigabit Ethernet 1. That's why here we mentioned about the adjacency seed needs to be preceded by the node seed. It needs to arrive to a certain node that can recognize this adjacency. Otherwise, it cannot be processed correctly. This requirement can be avoided by using a globally significant adjacency seed at the expense of having additional state in the network. Yes, if you assign it globally, then other routers also will identify this, but all the other routers will need to receive and keep this information. Adjacency seeds are essentially instructions to forward packet through a specific interface regardless of IGP metric or the shortest path consideration. It is like a policy saying that you have to forward the packet out this interface no matter what IGP cost it has or no matter which next hop the shortest path takes. In addition to node seed, Anycast seed, and adjacency seed, there is also another kind of seed called binding seed. A binding seed is bound to an SR policy, which may be expanded to a list of seeds. It can either be locally or globally significant. When a packet is sent through the network, the binding seed is used to identify the service or function that the packet should be directed. It is used in conjunction with other segments, such as prefix seeds and node seeds, to establish a path that directs traffic across the network. Upon receiving a packet with a binding seed as the top level, the router will pop the binding seed and then push relevant seeds that are associated to that binding seed. To me, I feel binding seed is like a function in programming that was programmed to do specific action. We can call the function whenever we want to do those actions without needing to rewrite the code. For example, you create a binding seed and saying that when the router receives this seed, then expand it to become following list of segments. So the router, when receive this packet, it will pop the seed and then it will impose the segment that you predefine. It is like a function in programming. Besides the IGP segments, there are also some BGP segments that ingress border router of an AS can steer a flow along a selected AS toward a selected egress border router of the AS and through a specific peer by using BGP egress peer engineering or EPE capabilities. BGP segments are classified as two categories. They can be a BGP peering segment that are recognized by BGP EPE enabled node for inter-domain path selection, or BGP prefix segment that identify the specific BGP prefix. A BGP peering segment can be a peer node segment represents a BGP peering node. A peer adjacency segment represents an adjacency to a BGP peering node, or a peer set adjacency segment that represents a set of BGP peering nodes. Basically, this one is for the ingress border router to select how you will forward the packet out to the neighbor AS. Let's say you want to use a specific link through a specific AS for this destination, then it can be implemented with this BGP seeds. For supporting BGP prefix seed, a new optional transitive BGP attribute is created for announcing the level information. It was originally defined for SRMPLS but now extended for SRv6. A BGP prefix segment is a BGP prefix which has a BGP prefix seed attribute attached on it. This is applicable to the MP-BGP, IPv4 or IPv6 level unicast prefixes. The label associated with the prefix is encoded in the NLRI of the BGP update using two BGP type length values or TLV, or label index TLV and the originator sRGB TLV. The label index TLV contains the label index value for the associated BGP prefix. It is a hint to the upstream BGP speaker about the incoming label to use for the prefix. And the originator sRGB TLV is an optional and contain information about the sRGB of the node originating the BGP prefix. It is an optional TLV. We finished the terms. There are many terms. But in reality, you don't have to memorize all of them because the main focus that we will talk about today, mainly the node seeds and the adjacency seeds. Just remember this. Node seeds for identifying specific node and adjacency seed for identifying specific interface. And we will make use of these in our lab. After trying to memorize many terminology and component of the segment routing in the previous part of the presentation, now we will get into something more practical, which is how the encapsulation and packet forwarding will work for segment routing with MPLS data plan or SRMPLS. When implementing SRMPLS, a segment is encoded as an MPLS label and an order list of segment is encoded as a stack of label. The active segment is the topmost label, and there is no change to the operation of the standard MPLS data plan for supporting segment routing. So actually, it will work the same for MPLS. Simply three operations: post, swap, and pop. For SRMPLS, earlier I think we mentioned about sRGB. It is a set of local MPLS label reserved for global segment. While it is a node-specific property, means this one, it can be different in every router. It is a global block. It is like the label range that we reserve for assigning the segment routing labels. It can be configured differently on different router, but normally to simplify the network operation, you can configure all nodes to be the same, then it is easier, it is simpler. I will give the example why. In this example here, the range is 16384 up to 32767. SRLB, as the name indicated, it is a set of local MPLS label reserved for local segments. And then in this example, this is the range. This range can be configured, but here I will say why we should configure to be the same throughout the network. Let's have a look at an example of label advertisement of an SR domain with a common sRGB range. Common sRGB range means every router we configure the same range. In this example, all nodes are configured with identical sRGB range and advertise only node seeds. All node seeds are allocated as absolute globally significant MPLS label values. There are 3 nodes in this network, P1, P2, and P3. Each node assigns an absolute label for its loopback address. For example, P1 assigns 101 for its loopback, and P2 assigns 102, and P3 assigns 103 for its loopback. This slide is showing the LFIP entry for the node seed of P3 on each node. Since all nodes sit in the same, in this example, are absolute labels, so every node will install exactly the same label for each individual node seed. We can see no matter in P1, P2, or P3, for forwarding to the node seed of P3, the label will be always 103. So this is the point. When we configure the same label range, then we can use an absolute value here. So we can say that for P3, 103, for P2, 102, for P1, 101. So no matter which router, it will always use the same label for forwarding to P3. That's why if you capture the packet, you will see when the packet traverses hop by hop, the label is not changed. It will be always 103, 103, 103 until arriving to P3. This slide is showing the LFIP entry for the node seed of P2 on each node. Same as the previous slide, all nodes are using 102 for forwarding to the node seed of P2. Yeah, because they all are using the same range. So this 102 is within the range of all the routers. That's why we can use an absolute value for P2. That's why no matter on P1's forwarding table or P2 or P3, all the labels will be 102. In label is 102, out label also 102. In reality, they do the swap operation, but because they are swapping from 102 to 102, so it looks like they are not changing the level. Same here for all nodes that are using 101 for forwarding to the node seed of P1. Yeah. So this is simple for segment routing with the same range. If you are using the same sRGB range, you can use absolute value, just assign a number for each specific node. Then this number will be globally significant throughout the SR domain. And then when you do the trace route, also when you see label 101, you know it is destined for P1. When you see label 102, you know it is going to P2. It's easy for troubleshooting also. That's why it is straightforward to have the same sRGB range throughout the SR domain. And in the case the node in the same domain are having different sRGB ranges, then in this case, the absolute value cannot be used. There might be some reason, for example, you are running different platforms that their supported ranges are not the same. Then in that case, you cannot use the absolute value. Then we need to use a globally unique index instead. So in this case, not an absolute value anymore, it will be an index. And based on this globally unique index value, each node will calculate its own local label by adding the index on top of the start of its range. Okay, let's see some example. For example, node A and node B are having different sRGB range configurations. In this case, if we happen to assign an absolute label value, this value may be covered by node A but not node B, or may be covered by node B but not node A. Because you can see they are having totally different range. The ranges are not overlapping with each other. So if we assign a value that covered by A, it will not be covered by B. Then we'll have problem. To solve this, we can assign an index instead of an absolute value. Let's say we assign an index of 100. It means that no matter what your sRGB range is, simply add 100 on top of the beginning of the range and assign your local label for this seed. In our example here, node A's sRGB range is 16384 to 32767. After adding an index of 100, its local label for the seed will become 16484. In contrast, node B's sRGB range is 65536 to 131,071. After adding an index of 100, the local label will be 65636. So you can see, simply we use the beginning of the range at this index of 100. Then we will get the local label value for each router. This is in the case that the routers are not having the same range. Here is an example of label advertisement with different sRGB ranges. Same as in the previous example. For simplicity, we will use only the node seed to demonstrate this. And all the node seeds are now allocated as the unique index values instead of the absolute values. This is because all nodes are having different sRGB configuration. So we can have a look at this diagram. There are totally 3 nodes, P1, P2, and P3. Each node assigns a unique index for its loopback address. P1 assigns index number 1 for its loopback, P2 assigns index number 2, and P3 assigns index number 3. The text might be small, but you can see here, index 1, index 2, index 3, that they assign for their loopbacks. And the slide is showing the LFIP entry for the node seed of P3 on all the nodes. Since all the nodes in this example are the unique index values, so every node will calculate its own label for each individual node seed based on the sRGB range configuration. We can see that P1 figure out that it should use 103 and P2 use 203 and P3 uses 303. Because the range of P1 is 100. So for the destination P3, the index is 3. That's why 100 plus 3 will become 103. And then for P2, its range is 200. So 200 plus 3 will be 203. For P3, its range is 300. That's why 300 plus 3 will be 303. And then finally, when they are coordinated, P1 will say, my in label is 103, but when I send to P2, P2 is expecting 203. And then P2 is saying that my label is 203, but when forward to P3, it is expecting 303. Basically, the label is calculated instead of being an absolute value like in the previous example. This is the LFIP for P2's loopback. Yeah, the same concept. The labels are calculated based on the own range. And same here, that all nodes are using different label values as they have different sRGB range. Just now we talk about node seeds, which are the transport labels for forwarding to a specific node. How about the service label like MPLS VPN? There is no change for this part. No matter with LDP, RSVP, or SRMPLS, MPBGP is still the protocol for exchanging service label in MPLS VPN scenario. So basically what we did earlier in session 2, we did LDP plus MPLS VPN with the VPN v4 unicast address family. When we implement segment routing, the BGP part does not change. Basically, we just remove LDP, put in segment routing, then the BGP part remains the same and it will work the same. Now we understand how nodes are assigning the labels in segment routing, we will move on to see segment routing use cases with different scenarios. Use case 1 is the ECMP aware shortest path routing. Node seeds are allocated and advertised with absolute labels, as all nodes in the SR domain are having identical range. We will use only node seeds to demonstrate this, and then they will be absolute labels because of identical sRGB range. Our objective is to deliver traffic between PE1 and PE2 through the shortest IGP path. For simplicity, all IGP metrics are set to 10 by default unless otherwise indicated. So on this topology, if we did not mention about the IGP metric, it will be 10, 10, 10, 10, except this one is 100. As we can see in the diagram, the link between P5 and 6 has a metric of 100. So as a result of this, the shortest path from PE1 to PE2 is through P1, P2, and P3. Since the node seeds are globally significant absolute labels, the MPLS label for reaching PE2 is the same in all nodes. Because this one, we just want to reach to PE2 with the shortest path. So it is similar to what we do in LDP. Then we don't need to put multiple seeds. Then in this case, we just need to put the destination seed of 222 for reaching PE2. And then because of they are having the common sRGB range, that's why in each and every node, they have the same label for reaching to PE2. Basically, PE1 will impose the label of P222, and then when arrive to P1, P1 will swap it from 222 to 222, and then continue. Here also will swap from 222 to 222, and then finally this one also will do the same. The actual traffic forwarding will look like this. In fact, there is a swap operation happen in P1, P2, and P3, but they are just swapping from 222 to 222. That's why we feel the label did not change. Use case 2 has similar setup as use case 1, except now each node has different range of sRGB. Therefore, we can no longer use the absolute label, and we need to use the index values. The objective is pretty much the same as use case 1. It is to deliver traffic between PE1 and PE2 through the shortest path. All point-to-point links have an IGP metric of 10, except the link between P5 and P6. So the shortest path is the same through P1, P2, and P3 to PE2. Since each router has its own sRGB range, so we are using index value rather than absolute values. Every node needs to calculate the label values based on their sRGB range plus the index. And as a result of this, the label values for the same node seed are different along the path because they are having different range. We can see PE1 pushes 222 for reaching PE2. When the packet arrives at P1, it swaps from 222 to 322. And when it arrives at P2, it swaps from 322 to 422. And when arrives at P3, it swaps from 422 to 822. The MPLS forwarding operation are actually the same, no matter for absolute labels or index values. The only difference would be the change of label value in each hop due to the different sRGB range. Actually, the forwarding mechanism is the same, but we just see the label change when the range is different. But when the range is the same, then it looks like always 222 along the path to the destination. In use case 3, we will demonstrate a traffic engineering path using segment routing. Same to use case 1, the node seeds are allocated and advertised with absolute labels. So in this use case, it will be absolute labels, not the index. Because all nodes in the SR domain having identical sRGB range. Unlike the setting in use case 1 and 2, all IGP metrics in this use case is 10. without exception, which means the IGP shortest path from PE1 to PE2 should be an ECMP through P1, P2, P3, and P4, P5, P6. I mean, in case we don't do traffic engineering, if we just take the shortest path to the destination, from here to here, there are two ways to go. Can be this way and this way, because they are having the same metric. Here is 10, 10, 10, 10, so 40, and here is 10, 10, 10, 10, also 40. So it will be ECMP. However, the objective of this use case is to establish a traffic engineering LSP for PE1 to reach PE2 through P2, but avoid the point-to-point link between P2 and P3. So the requirement, we need to go from here to here. We want to go through P2, but we don't want to use the link between P2 and P3. So that's why as a result of this, the path will look like this. So how to implement this? Since all node seeds are absolute labels, so the label values are the same on every node. If we simply push the label 222 in PE1 like in the use case 1, the traffic will just follow the IGP shortest path, will go ECMP two ways like this to PE2. So this is not what we want. So let's think about how we can actually steer the traffic through P2 and P5. Can we first steer the packet to P2 and then direct it further to P5? Yes, this is exactly the solution. For establishing this traffic engineering LSP, PE1 will need to push 3 labels instead of 1 label. The label stack should be 102, 105, 222, and 1234 is the service level. So we don't count this one. So you can see 102 is for arriving to P2. And then after that, P2 will remove 102, will pop 102, because this segment has been completed when it arrived to P2. And then after that, P2 will forward to P5 using the top level of 105. So 105 will expose to P5. Then because of P5 is the destination for 105, it means that the segment of 105 is completed. That's why P5 will pop 105 and then forward it further through the shortest path to PE2. In this case, P6 does not remove 222. Instead, P6 will swap 222 to another 222, because P6 is not the destination of 222. So from P6 point of view, it is still on the way to the destination. That's why I just need to swap it. I will not pop it. This is how traffic engineering works in segment routing. And the traffic engineering path is directly encoded onto the packet by the head end using a stack of MPLS labels. This eliminates the need for signaling and state tracking in every node along the path. So all the routers along the path, they don't need to keep track of this LSP anymore, not like RSVPTE. If we are using RSVPTE, basically P1, P2, P5, P6 will need to have a status on the router to take note that there is an LSP traveling through it. But in this case, because we use the label stack like this, PE1 simply give the instruction on the packet header. So along the path, it will be just MPLS forwarding based on the label. There is no instruction needs to be stored in any router saying that this LSP exists. Okay, next, use case 4 is also about traffic engineering. The difference from use case 3 is that the point-to-point link between P5 and P6 now has an IGP metric of 100. Also, we will have adjacency seeds in addition to the node seeds in this use case. All seeds are allocated and advertised with absolute labels because I want to try to make it simple. So I will use absolute labels to do the example here. Otherwise, if we are talking about index value, we need to calculate the index based on each router's range. All nodes are having the same sRGB range, so we use absolute labels. The objective is pretty much the same as use case 3. But now, since the IGP metric of the link between P5 and P6 is 100 now, so P5 shortest path to PE2 is not through P6 anymore, but instead it is through P2 and P3. Remember previously in the previous example, we say that go to P2, then go to P5, and then go to PE2. It is okay because when it arrives to P5, P5 found that PE2 is through P6. This is okay. But in current example, when the metric is 100, then from P5's point of view, in order to go to PE2, it's no longer through P6 because here and here combined together will be 110. But going this way will be only 30. That's why P5 will loop the packet back to P2 if we don't do the additional instruction. That's why in this case, we need to make use of the another seed called adjacency seed. Adjacency seed, for example, from P5 to P6, we will define an adjacency seed of 1001 for this specific interface. So when we make use of this adjacency seed, it will simply tell P5 saying that regardless of your IGP metric or shortest path, you simply push the traffic out through this interface to P6. Don't care anything, just push it out through this interface. Yeah, in case if we were to employ the same solution as use case 3, it will happen like this. It will not go to 6 because the shortest path from P5 is through P2 to PE2. To solve this problem, we utilize the adjacency seed of 1001. Instead of pushing 102, 105, and 222, now PE1 need to push. Confirm your speaking language. What is it? I'm speaking in English. Instead of pushing 102, 105, and 222, PE1 is now pushing 102, 105, and additionally 1001 here. There's one more level here. The 1001 followed by 105 is the adjacency seed for the point-to-point link between P5 and P6. When the packet arrives at P5, it will first pop 105 as it is the destination for this node seed. So basically, when the packet arrives to P5, for this part it is the same, so I did not repeat. When arrived to P5, P5 will first remove 105 because it is the destination for 105. It means that the segment of 105 completed its mission. It arrives to P5. But next, it will process the adjacency seed of 1001 here. Then it will find out that this 1001 is referring to this link. So P5 will forward the packet through the link to P6 regardless of IGP metric and shortest path. The whole instruction is like saying that P1 first, you should take the shortest path to P2, then take the shortest path from P2 to P5, then go through the P5's point-to-point link with P6, and then take the shortest path from P6 to PE2. Let's see one by one. 102 means come to here first. 105 means after coming to here, go to P5. And then after arriving to P5, 1001 means go out through this interface. And then finally 222 means you just take the shortest path to PE2. Because from the P6 point of view, there is no other shortest path besides this point-to-point link. So it will just go to PE2 this way. Use case 5 is also about traffic engineering, but with the involvement of APNIC seeds. All seeds are allocated and advertised with an absolute value because all nodes in the SR domain are having identical sRGB range. So this is the case of APNIC. An APNIC seed typically has one or more members. it allows ECMP-aware shortest path forwarding to the closest node of the anycast set. All the router in the anycast set advertise the same anycast prefix with the same label value. The goal of this use case is to ensure that traffic from PE1 to PE3 follows the top plan, specifically the anycast group A that has the seed of 100. So in this case, we can see we group these four routers as an anycast group A, and then we will assign a prefix for it and a seed for it. This seed is 100, means A1 also 100, A3 also 100, A2 also 100, and A4 is also 100. And then we don't care. Basically, we just want the traffic go through the top plan. No matter it is through A1 or A3 or A2 or A4, just go to the nearest one from the source. So in this case, we can use the anycast seed. To achieve this, PE1 can push the label stack of 100 and 113. The top level of 100 is the anycast seed of the anycast group A, indicates that the packet should take the shortest path to this anycast group A. So yeah, 100 is for arriving to here. Because PE1 is nearest to A1, so it will arrive to here. But in case if PE1 is nearer to A4, then it will arrive to A4. It doesn't care which router the packet will arrive as long as one of these four routers. Upon the packet's arrival at the members of anycast group A, the receiving router will perform a pop operation. Yeah, because when the packet arrives, then the receiving router will see, this segment 100 is completed. It arrived to us already. So it will pop the label, removing the 100. And subsequently, the top label will become 113, representing the node seed of PE3. So it will send to PE3 with the shortest path. The 5 use cases that we have just explored provide a practical demonstration of segment routing applications. Now, in this part of presentation, we will take a closer look at the details of traffic engineering within the context of segment routing. I'm sorry, I might take a little bit longer than the session time because now I see the time is 2:58, but I guess I might need to take 5 or 10 minutes more for the presentation. So we will be a bit late to go to the break. So this part, we will talk about traffic engineering within the context of segment routing. Traffic engineering, or TE, is an ability to steer the packet along specific path that may not be the IGP shortest path based on a range of criteria such as IGP metric, TE metric, latency, loss, and link colors. An SLA or service level agreement is usually expressed as a desired business outcome. It may also be referred as a service intent. And a color in the traffic engineering world is an opaque quantity associated with an SLA or a service intent, which supports the realization of the SLA in the network. This is an example topology demonstrating an MPLS VPN service carrying traffic between CE1 and CE2 through the provider routers of PE1 and PE2. Let's assume that all the IGP metrics are 10 unless otherwise indicated. As shown on the diagram, technically there are 3 possible routing paths from PE1 to PE2. For example, the blue path below, this one, the blue path below, is the shortest path from PE1 to PE2. This blue is a color name for us to identify a specific SLA or service intent. Besides the blue path, based on the diagram, there are another 2 paths, purple and red. The purple has more hops along the path, but it is a low latency path. The red is an example of traffic engineering path that has a constraint of using only the green links to establish the LSP. It may be a bit confusing here because blue, purple, red, and green all appear to be color, but you can see In fact, the blue, purple, and red, they are the name of the SLA. The blue is the shortest path, the purple is the low latency path, and then the red is the restricted path that uses only the green link. And the green is a group name of the links. I know it is confusing, but the original author of the slide wrote like this. So I have to present it this way. Okay, let's examine each of the paths. The blue path is the IGP shortest path. This scenario is simple. Only a single transport level, which is the node seed of PE2, will be needed for establishing this LSP. Then the traffic will follow the ECMP aware shortest path to the destination. This is quite simple. It is like the use case one that we did. It is the shortest path. The purple one is traffic engineering low latency path. Although it traverses more intermediate nodes than the shortest path, but its overall latency is lower than the shortest path. Let's believe it is like this because the diagram is saying like this. Okay. To establish the LSP for this low latency path, several seeds will be required to override the shortest path forwarding. The path is fully expressed as an order list of intermediate nodes plus the destination node. So totally we will use 3 labels, 104, 105, and 222, which are the node seeds of P4, P5, and PE2. So you can see 104, 105, 222 means go this way, then this way. It is a traffic engineering path. While a full list of segments will work, there is a way to slightly optimize the segment list. Instead of having 3 labels, the segment list can actually use only 2 labels. Now we are talking about the possible optimization. Instead of using 3 labels, we can use only 2 labels like 105 and 222, which are the node seeds of P5 and PE2. Because the shortest path from PE1 to P5 will be through P4 anyway. So the label of P4 is not required in this case. I mean, technically we can put 104, 105, 222, but it is not required because the only way for PE1 to go to P5, the shortest path is through P4. That's why we can directly say that, hey, PE1, you take the shortest path to P5, then from P5, take the shortest path to 222. This is the optimization that we can do. The last one in our example here is the red path. It is a traffic engineering path that uses only green links, which are the PE1 to P1, P1 to P2, P2 to P3, and P3 to PE2 links. Well, personally, I feel it might make more sense to call this a green path than a red path because it is using green links, right? Anyway, the original author of this presentation wrote this. So let's move on with the red LSPs that uses the red LSP that uses the green links. Similar to the previous purple path, the label stack of this red path can include all node seeds along the path. So PE1 will push 101, 102, 103, and 222. 101 is P1, and then 102 is P2, and then 103 is P3, and then 222 is PE2. Totally 4 transport labels. But is it necessary to have all the 4 node seeds along the path? Can this be simplified? Think about it. Yes. We can use an optimized segment list with only 2 labels, 102 and 222, which are the node seeds of P2 and PE2. So that PE1 will take the shortest path to P2 first, then take another shortest path from P2 to PE2. In this optimization, we remove 2 labels. We remove the label of P1 and P3. And we kept only P2. Think about that. Why is the node seed of P2 required in the segment list? Why can't we remove P1 or P3? Can we? Can we remove P1 or P3? Can we keep P1 or P3 and then remove P2? if we use P1 instead of P2, from PE1 to P1 is fine. Yeah, because from PE1 to P1, they are directly connected. So this will be the shortest path. This is fine. But from P1 to PE2, it's not sure that it will go this way. Because from P1, it can go one hop, two hop, three hop, or it can go one hop, two hop, three hop to PE2. So that's why if we use only P1, then it will have the equal cost path. And for the case of using P3 also will have similar problem. From P3 to PE2 is fine. From P3 to PE2, it is directly connected. It should be okay. But from PE1 to P3, then this is not sure. It has one path, one hop, two hop, three hop like this. It has another path, one hop, two hop, and then three hop. So it has ECMP from PE1 to P3. That's why P2 is the only intermediate node that can make sure the traffic forwarding stays on the green links after optimization. To realize the traffic engineering routing behaviors, there are a few solutions that can be used, like SR policy, flag algo, and seamless MPLS. SR policy provides capability to construct intent-aware paths in both intra-domain and inter-domain environment. Flag algo or flexible algorithm allows us to create separate topologies that can be used for path calculations. It is an IGP feature and therefore it focuses primarily on intra-domain routing. Seamless MPLS is a scalable solution utilizing BGP level unicast for integrating multiple IGP domains as a single end-to-end MPLS domain. In the case, let's say you have a segment routing domain, and then you have an LDP domain, and then you would like to connect these two together, then seamless MPLS is one solution. Sure, later in this presentation, I also will talk about the interworking between SR and LDP. It will be the next part of this presentation. But I think maybe before the next part of the presentation, I will just quickly finish this traffic engineering part and then we will have a break first. Just now we talk about optimization. Why is it important to optimize the segment list? Because each hardware platform typically has its limitation on how many levels can be imposed or processed without having significant performance impact to the forwarding. This limitation is known as maximum segment depth or MSD. It is important to understand the MSD while computing the segment list. There are some mechanisms to reduce the size of the segment list, and they are critical to ensure that the network is able to support the traffic engineering part. So that's why technically we can use a full list of segments, but ideally we should optimize. Then it will avoid the situation that maybe the hardware platform cannot support so many levels. Depending on the network setup, the MSD can be signaled to the controller using a few methods. The first one would be through Path Computation Element Communication Protocol or PCEP if it is used between head-end router and the controller. In the case the controller does not speak PCEP, technically it is possible to let the controller participate in the network's IGP so that MSD information in the link state database will be visible to it. However, this option is not recommended as all IGP events will also be visible to the controller. And the controller may directly impact to the stability of IGP if anything is wrong with it. So we don't recommend to let the controller join the IGP and become part of it. Alternatively, we can use MP-BGP with link state address family known as BGP link state or BGP-LS, which can re-advertise the MSD values that the IGP advertised to the controller. This option is more scalable thanks to the support of route reflection and also out-of-band setup that BGP can offer. Imagine we have multiple IGP domains in our network. We just need to have one BGP-LS router in each of the IGP domain. Then all of them can peer to a centralized and out-of-band route reflector. This route reflector will re-advertise everything else to the controller. By the way, PCE here on the diagram stands for path computation element. It is the controller that we are talking about. So when you are using controller, instead of letting the controller participate in every IGP, this can be the solution. Use BGP to re-advertise the MSD information, and then you can make use of the route reflection. And this route reflector can be our fan. It doesn't have to be in the network path. It can be a server somewhere else. To enable traffic engineering capability, IGPs like OSPF and ISIS are updated to support traffic engineering extensions that are created to advertise additional information for the computation of the TE paths. This information is used for the routers in the network to construct the TE database. Besides the base information, there are also traffic engineering metric extensions that can further distribute performance information of the network, such as latency, packet loss. Because in IGP, we only distribute the metric of the link. But with this extension, then it can distribute further with some other information like latency and percentage of packet loss. Here is a list of traffic engineering extensions that have been defined for OSPF v2 and ISIS. You may find out more details about them by reading the RFC listed at the right column of the table. And here is another list for traffic engineering metric extensions that have been defined for OSPF v2 and ISIS. The metric extensions for OSPF v2 were defined in RFC 7471, and for ISIS, you can refer to RFC 8570. Talking about traffic engineering extensions, RSVP-TE was originally the only consumer of the TE attributes, but now it is no longer the case because now we have segment routing. And because segment routing like SR policy and flag algo also need to make use of the TE attribute, therefore TE extensions are now required to support multiple applications with the capability of indicating which applications are using the link attribute advertisement on the link and advertising the application specific values for the same attribute on the link. Basically, with this extension, we can achieve, like in flag algo, we can have multiple topologies for different purpose. Let's say you have 20 routers in the network, you can create a topology for low latency with 10 routers in it, and then you can create another topology for the high throughput with, let's say, 12 routers in it. You can have different topologies with the support of this extension. As a result of this requirement, RFC 8919 and RFC 8920 introduced the application-specific link attributes, or ASLA, for OSPF and ISIS respectively. By the way, for all the RFC that I mentioned along the way of presentation, in fact, I listed them in the references here at the last part of the presentation. So if you would like to read more about the RFC, actually all are listed here. Anyway, before we continue to the last part of the presentation, I think it is time to let everyone have a break because we are 14 minutes late. So now we will have a break and I will continue at 3:30 again for the last part of the presentation and also the lab for the segment routing. Hope to see you all again at 3:30. And for the people who did not pick up the socks, we have some more available here along with some few pens and some of my business cards. Okay, thank you very much for joining this session. Okay. Also, for any of you who did not check into the session, please check into the session to confirm your participation of the session. Thank you. Sorry for the short break, but it is time to continue. And as a reminder, on behalf of APEN, please don't forget to check in the last session at 3:30. You can check in on the webpage or using the app. Also, before we continue, let me request everyone, if you are okay, please provide a survey feedback for this training by using this link. Basically, it will ask you only some questions about what do you think about this training, what we can improve, or what you like about this training, any suggestion, then please help us to fill in the survey form to provide your feedback for this training. Or if you would like to have other trainings, also feel free to add it in the survey form. There is a question about what are the training topics that you would like to suggest. You also can add it in the survey form. Okay, so let's continue. After knowing what segment routing is and its application, next we will talk about the interworking with LDP. Imagine we have a network that has partially enabled SRMPLS while the remaining part of the network is still using LDP. Then how should we do to integrate them? It is a two-way integration that we need to consider. The first one is LDP to SR interworking, which we need to distribute the labels from the destination in the SR domain into the LDP domain. A node that has both SR and MPLS, SRMPLS and LDP capabilities will, with the active LDP peers, can create LDP binding for each prefix seed and node seed that it learned in the SR domain. Then it can map the incoming LDP label to the outgoing SR label. This is LDP to SR path. Another one is SR to LDP interworking, which we need to advertise seeds for destination in the LDP domain into the SR domain. This will require the use of a segment routing mapping server or SRMS. SRMS is an SR-capable router that advertises mapping between prefixes and labels for the prefixes that it does not own itself. So it is like a proxy advertise the prefix and label on behalf of other people, because the people in LDP, they cannot advertise their prefix in segment routing domain. So that's why we need segment routing mapping server to do on behalf of them. Yeah, in another word, it is advertising the prefix to seed mappings on behalf of non-SR capable routers. To achieve this, the SRMS will require to have IGP extension that support segment routing. Since this is a control plane function only, the SRMS does not have to be in the data path and can be located anywhere. So yes, technically you can have a dedicated router to run as the SRMS, it doesn't have to be on the path. And multiple SRMSs can be used for redundancy purpose. Let's have a look at an example of interworking with this mixed SR and LDP network. The left side of the network with blue background is SR domain. All nodes in blue are SR only. The right side of the network with green background is LDP domain. All nodes in the green are LDP only. There is a node in between, which is P7. This P7 is running both SR and LDP. Imagine if you have a requirement of setting up a contiguous LSP from PE1 to PE3 and from PE3 to PE1, then how should we do? First, let's settle LDP to SR interworking. This requires a node that supports both SR and LDP, and the only candidate in this network would be P7 because all the other routers at the left, they support only segment routing. All the other routers at the right, they run only LDP. So P7 is the only one that is running LDP plus segment routing. To distribute the label for destination in the SR domain into LDP domain, P7 needs to create LDP binding for all SR prefix seeds and node seeds, then update its LFIP to use the SR labels as the outgoing label for those destinations. This is not very complex because normally LDP, by default, LDP will assign the label for IGP route anyway. The actual traffic forwarding will look like this. From PE3 to P7, LDP labels will be used for forwarding. When the packet arrives at P7, it will swap the label from LDP label to the SR label. So we can see this part is using the LDP label until arrive to here. And then P7 will swap 701 to 101. 701 is the LDP label that it assigns for this destination. And 101 is the seed that advertised by PE1. For the case of segment routing to LDP interworking, we need to have a segment routing mapping server or SRMS. This can actually be any router from the SR domain, but let's assume we will use P5. As the SRMS P5 will advertise seeds for LDP only nodes, such as P8, PE3, and PE4. Then after that, all nodes in the SR domain will use the label that P5 advertises to reach those destinations. So we need to configure P5 to advertise the label for P8, PE3, PE4. The actual traffic forwarding will look like this. From PE1 to P7, the SR labels will be used for forwarding. And when packet arrive at P7, it will swap from SR label 103 to the LDP label of 803. Then from P7 to PE3, LDP labels will be used for forwarding. This part will be segment routing labels, and then this part will be LDP labels. And then here, P7 will swap from this one to this one. And then the reason why all the routers can know the labels, it is because of P5 is a segment routing mapping server that it advertises the label on behalf of those people who are not in the segment routing domain. Okay, so finally we finished the presentation. Here are some references that have been used for creating this presentation. The items are listed in the order that we talk about them in the presentation, starting from what is segment routing until MSD, until application specific link attribute and interworking. You can find the details in these RFCs. Actually, there are much more to say about segment routing, such as traffic engineering with SR policy, flexible algorithm, and seamless MPLS. resiliency with loop-free alternate, or we call LFA, and remote LFA and topology independent LFA, as well as BGP egress peer engineering. Segment routing with IPv6 data plan or SRv6 is also another wide topic that we are not able to cover today. In fact, the entire SRMPLS presentation, only this SRMPLS presentation has more than 300 slides because we will have another 100 slides for SR policy, flexible algorithm, and seamless MPLS. Also, in addition to this, SRv6 has another 300 plus slides. That's why we cannot fit all the thing into the limited time today, but I try to trim the presentation down and give you some brief summary and introduction. At least you can understand what segment routing is doing and how it works on MPLS data plan. I hope the training today will be beneficial to all of you. If you have any question after the training, also feel free to reach out to me. Now we finish the presentation part. Next, I will move into the lab part that we will do the segment routing lab with APNIC Academy. For doing the lab, actually, it will be similar to what we did earlier. We will need to use the APNIC Academy website. Let me open the website and share the screen. And meanwhile, if you have any question, you can raise. Okay, so I will go into our course material page, and then on the course material page, there will be a link for accessing the lab. This is segment routing with OSPF v2 with Cisco IOS XE. In fact, besides this, we also have another lab, which is MPLS LDP and segment routing lab with Cisco IOS XR. So for the people who are using iOS XR, if you would like to try it out, you also can try this lab. Now I will go to this lab and do the live demo how we can configure segment routing in Cisco with OSPF v2. To launch the lab, we need to log in to APNIC Academy website and then go with the link listed in the course materials and then click launch lab. Then I need to switch the screen share. Just a moment. It will take approximately 1 minute to load the lab. If you are interested, you can do together, or otherwise you can also do it later when you have access to your computer or when you have free time. Because actually all the labs are available 24/7. You can use it anytime. You just need an APNIC Academy account to access. First of all, about this lab, the lab is designed for us to configure the segment routing on Cisco CSR 1000V cloud routers. And there are 3 tasks. The first one will be the base segment routing configuration. The second one will be using seed index value with different sRGB on all the routers. These 2 are quite basic. Basically, they are like the use case 1 and use case 2 that we demonstrate earlier in our presentation. Will be mainly the short test part, and then this is just one with the common sRGB range, another one with different sRGB range. And then task 3 is the segment routing traffic engineering tunnel. This one we will do the manual configuration for traffic engineering. In reality, you can do traffic engineering with an SDN controller, But in this lab, we will not use the SDN controller. We will just do the manual configuration to show how it works. It will take some time to boot the router. Maybe it will take a few minutes. And this is the topology. It is quite straightforward. You can see R1, R2, R3, R4, R5, R6 like this. Basically, they are the full mesh routers. Yeah, full mesh X R1 to R6. And in the lab, if you cannot complete the lab, then you can use the save option to save this lab to continue to do it within 7 days. This will save your progress, and within 7 days, you can continue. Also in the lab for the sample configuration, usually we will have the description like this. Starting with the exclamation mark, it is for explaining what this command is used for. For example, configure terminal, it is the command for entering configuration mode like this. There are checkboxes in each section of the lab. You can tick the checkbox just for tracking your progress to make sure that you know where you are in the lab. And here there are some links like iOS R1, R2, R3, R4, R5, R6. When you click on it, it is switching the console from one router to another. For all the routers, they can be logged in with APNIC username and the password training. And for Cisco enabled password will be lab config. When accessing the router, we can use the command enable. Then it will ask you to type in the password, then just type in lab config. Then you will be able to start the configuration. And as part of the best practice, we have some configuration that pre-apply to the router, such as to disable some unused services and to set the host name. These are the configurations that we have applied to the router. And in here, you can see the addressing plan. Basically, 10.0.0.0/24. This is the range for loopback. And then the range for point-to-point will be 10.1.0.0/24 and /30 per link. The first host IP is for the router with the lower number, and then the second host IP will be for the router with the higher number. So you can see from router 1 to router 2. Let me switch the screen share to the diagram. From router 1 to router 2, /30 here. Dot 1 will be router 1, dot 2 will be router 2, because the first IP will be for the router which has the lower number. And the second IP will be for the router which has a higher number. Now the routers are loading. And by the way, for your information, IPv4 and OSPF v2 configuration have been applied as the initial configuration of all the routers because the main focus of this lab is segment routing. So we don't want the participants to be busy with configuring the point-to-point link, OSPF. We assume that all of those things are completed in advance. So you just need to apply the segment routing configuration. Okay, now since the routers are loaded, so I will start from task 1. Task 1 is the base segment routing configuration. There are 3 steps. The first one will be the configuration. The second one will be verifying the basic configuration. And then the last one would be verifying the forwarding. And this is the information about the label range that we assign for configuration, for this configuration. R1, R2, R3, R4, R5, R6 all have the same label range. So it means that we can use the absolute label value for each node seed. We don't have to use the index. In this case, we can assign 16001 for R1, 16002 for R2, and 16003 for R3, so on and so forth. So we just use the absolute value only because the range is the same. Now let me go to R1 and start the configuration. First, I will need to log in, and then I need to enable with the lab config password. And by the way, here there is a T. I believe the people who joined my session this morning already know about that. In case you don't know, just for your information, when you don't want to type the command, you want to directly apply the command, you can press on T. It will copy and paste this command to the console directly. So configure terminal. And then for enabling segment routing, we need to enable these commands: MPLS traffic engineering tunnels and segment routing MPLS. And then we need to configure the global block, the sRGB. And then we need to configure to advertise the seed for PE for router one. For router one, the seed is 10.0.0.1/32. And then we will assign an absolute value of 16001. So we will apply this configuration. And then in OSPF, we also need to enable segment routing. We will go to the OSPF process and then apply segment routing MPLS, segment routing area 0 MPLS, MPLS traffic engineering router ID loopback 0, and traffic engineering area 0, and MPLS OAM. Then that's it. We can save the configuration. This is for router 1. Basically, for all the routers are having similar configuration. We can see router 2, 3, 4, 5, 6 also similar, except the prefix and the seed that we assign are different. So after router 1, I will apply the same configuration to router 2, 3, 4, 5, 6. For router 2, I need to log in. And with lab config, I will copy and paste the configuration. But for the people who are still learning, and if you want to practice the command line, don't do copy and paste like me. I just want to quickly show the configuration and verification. Also, when you are doing copy and paste, be careful. Sometimes due to the high latency on the console, maybe the place that you are accessing APNIC Academy might be far from the server. So in that case, the console will have the delay. So when you copy and paste, there might be some missing character that potentially will cause the command to be wrong. Then in that case, make sure you verify each command that you paste in. And this is for router 3. Router 3 also, I will apply the same configuration, mapping 10.0.0.3 to 160.0.0.3. Next, router 4. The configuration is almost the same, mainly the prefix and the seed number are different. And then next, we need to go to router 5 and repeat the same thing. We'll paste the configuration. Mainly here prefix is 10005, which is the loopback of router 5 with the absolute value of 16005. And next will be router 6. Router 6 also, we will enable MPLS and assign the prefix with the seed number of 16006. That's it for the step 1. Then the next step will be the verification part. We will verify the MPLS and OSPF information in this step. For R1, first of all, we will verify the MPLS label range, whether it is using the label range that we configure. Yes, it is. It is using 16,000 to 23,999, the label range that we configured. This is important because we are using the absolute label. So make sure all the nodes are using the same label, which is 16,000 to 23,999 in this lab. And next, we will check the MPLS forwarding table by show MPLS forwarding table command. Here we will see the labels are assigned. So you can see without LDP, we also can assign the label and distribute the label using OSPF. Because now OSPF and ISIS are extended to support segment routing. So actually, if the router is supporting segment routing, you don't have to run LDP anymore. You can simply turn on segment routing and then turn off LDP. Here there are many explanations here. I suggest to go through it if you are doing the lab. Then this command here, show IP OSPF database opaque area self originate. It is showing the OSPF LSA that we originated for segment routing. Here it is showing the label range starting from 16,000 and then the range size is 8,000. So basically it is 16,000 to 23,999. Also here in the link state database, we can see the prefix 10001/32. It has a seed ID of 1. Why? Actually, in OSPF, it is advertising as the index. Although we assign 16,001, it is advertising the index of 1. And then when combined together with the range, it will become 16,001. The same verification can happen on all the routers like R2, 3, 4, 5, 6. Maybe I will just quickly run through all of them. For R2, we can show and make sure the MPLS label range. Yes, it is correct. Then we can go to show MPLS forwarding table. We can see the label. Here you can see for router 2, for the same destination to 10.0.0.1/32, it is having the same label as router 1. When you go to router 1, I will switch to router 1 and then show forwarding table again. Maybe I need to show in MPLS finding. Show forwarding table. No, because R1 it is a router that directly connected to 10.0.0.1. So it in its forwarding table is not showing this record. Let's see another example. For example, if it is the destination of 10.0.0.4, router 1 is seeing 160.0.4. And then in router 2, it should see 160.0.0.4 the same. Yeah, here 160.0.0.4 because all the labels are the absolute values. So it is the same on all the routers. And then on router 2, we can continue the verification by showing the OSPF database. We will see the same. The range is starting from 16,000 and then totally there are 8,000 labels in this range. Also, the prefix of 10.0.0.2/32 is with the seed index of number 2. As I said earlier, although we configure it as an absolute value, but in reality, in the routing protocol advertisement, it is advertised as an index. And when combined with the sRGB range, then the result will be the same on all the nodes. The same verification can be on router 3 also. We can show MPLS label range and we can show forwarding table. Yeah, we have the same label for the 10.0.0.4, which is 160.0.0.4. And then show OSPF database. Then, yes, we have the same label range starting from 16,000 and totally 8,000 labels. Also, I believe I scroll past it just now. Yes, 10.0.0.3/32 has an index of 3 because we assign the absolute label of 160.0.0.3 and then when translate into the link state database, it is advertising the range of 160.0.0.0 plus an index of 3. Then we will verify on router 4. Router 4, we will run the same command. The range is the same and then show forwarding table. We can see all the other labels are the same as other routers except it doesn't show the label for itself because router 4 will forward to itself using the regular IP routing. It doesn't need MPLS. That's why in here it does not show 16,004 for itself. And if we show the OSPF database, we will see the same thing, starting from 16,000 with a range of 8,000, and its own prefix is with the index of 4, which is 160.0.0.4, because the range started from 16,000 and then plus the index of 4 will be 160.0.0.4. Next will be router 5. You might see actually in the verification that the instruction is very detailed and going through one router by one router slowly. Because actually this lab also it is designed for the participant to do it self-paced. So when you are doing it alone, it will be helpful for you to have the full instruction with all the verification steps. Yeah, this is 16,000 to 23,999. And the forwarding table, yeah, it is correct. By the way, on the forwarding table, you might see some entries here have the word A. A means adjacency seed. It means that if you are directing the traffic to those specific point-to-point links, then they will use these label numbers. I believe because in our router, we configure only the global blocks. So that's why here it is automatically starting from 16. because the adjacency seed is not the focus of this lab anyway. Uh, Here, when we show the database, we will see the range is 16,000 with the size of 8,000, and then prefix .5 is with the index of 5, which is together it is 16,005. The last one would be router 6. Router 6, we can run the same verification command. Then we see the range, and then we can run the same forwarding table command. We see the same labels, and then we show the database. Then we see the range, the size of the range, and the seed of this specific prefix, which is the index of 6 plus the range of 16,000, then it will be 16006. So this is the second step that we verify the control plane information. Next, we will verify the data plane. Then we will, I believe in here, we will do some forwarding test here. I will go to router 1 and then go through the steps. Let's say we want to use router 6 as the destination to verify the forwarding. Then the first one would be we can see whether it appears in the forwarding table or not. Yes, it appears in the forwarding table. In label, it's 16006. Out label also 16006 because it is an absolute label. And then if we show the details, it will show more detailed information about the path that we can use. Basically, this is an ECMP path. And then if we show IPCEF, it will show you which label the router will impose when forwarding to the next hop. For the segment routing, most of the time you will see the same labels unless you are using the different sRGB. Otherwise, it will be the same label. Then next, we will do the ping. We will do the MPLS ping. Actually, even you do the normal ping also okay, but just MPLS ping has the extra option for you to mention the label and the interface to do more advanced tests. So let's do the ping, and then the ping is successful. And then this is the trace route. The trace route is successful also. Yeah, and here it is. I think it is the test on each router. Router 2, 3, 4, 5, 6. When you are running through the lab, I think you can just run through those steps. Basically, we will verify the forwarding table, we will verify the CEF, and then we will ping, we will trace route. Yeah. Okay, so task 1 is basically like this. And then in task 2, we will use an index instead of an absolute value, which means in this case, each router will have different sRGB range. We will configure the different range. And then because this task 2 is based on the configuration that we have applied in task 1. So in order to apply the configuration for task 2, we need to remove some configuration from task 1. For example, task 1, we configure 16,000 to 23,999. We will now use no to remove it, and then we will add the new range. So let me just copy and paste the command one by one. Remove the global block configuration and then put the new one. And then now we remove the absolute label now. and then instead we put an index. So actually you can see the command is pretty much the same, just change from absolute to be index. And then after that, we need to save the configuration and we need to reload the router to, to make sure that the old label will disappear. For R2, R3, R4, R5, R6, I will do the same, but I will speed it up by just copy and paste the whole block of configuration and reload them directly. For R2, and then reload, yes. And then I will go to R3, then configure it, and reload, then R4, and then R5, R6. I think the reload will take a few minutes. So during these a few minutes, if you have any question, you also can ask while we are waiting for the router to reload. I just go through each router and press enter to make it go faster. Otherwise, it will show press any key and then show several times before it boots. After reboot, maybe we can go through the verification command here. Like in router one, we will show the red label range, we will show forwarding table, and then we will show the OSPF database, like what we did in the previous task. Besides router one, we also will verify this on all the router 2, 3, 4, 5, 6. Yeah, let's wait for it to boot up. By the way, one of my friends, he likes to press enter when the router is booting. And I asked why. He said he feels it will be faster after he pressed this. Okay. So now router one is booted, and then let me log in again. Router one, and run the verification command. Now we can see it is using the new range and the forwarding table. Okay, now with the new forwarding table, we can see the labels are different now. The in label and out label and out label to different neighboring routers also, they are different because now each router is having its own sRGB range. Here there are a lot of explanations. When you are doing the lab, you just go through it. And then let's show the OSPF database. Then we can see now, actually in OSPF database, we can see the structure is the same, no matter you use the absolute label or you use the index, it is still saying that the range is like this, and then the prefix is using the index of this one. And next, let's go to R2. Can show the label range. Yeah, it is in different range. And then we can show forwarding table. We can see they are having different labels. And then we can show in OSPF database. Then we will see it is advertising that its label range is this one with the size of 1000. And then its prefix is using the index of 200. Then if we go to check in router 3, router 3, the range is, yes, 18,000 to 18,999. And then the forwarding table, okay, they are using different labels. And then the OSPF database, yeah, the range is encoded in the database and the index is 300 is correct. For router 4, we will do the same verification. We see the range, we see the forwarding table, and then we see the OSPF database. Then we see the range is 19,000 with the size of 1,000 and the index is 400 for the loopback. For router 5, router 5, the same, the range is 20,000. It has its own range, and then forwarding table is showing different labels. OSPF, we can see the size is 1,000, the range starting from 20,000, and the index of the prefix is 500. Finally, router 6. 21,000, and forwarding table, they are having different labels. And OSPF, yes, the range of 21,000 with the size of 1,000, and the index for the loopback is 600. So can say all the verification completed. Then the next step, we will test the data plan part. The data plan, basically, we we can verify the forwarding table for a certain destination. Let's say, oh, this is on router 1. I will skip router 1, 2, 3, 4, 5, and then I will focus on router 6 because the verification commands are pretty much the same. So I will directly verify on router 6. Router 6, we will check the forwarding back to router 1 because router 1 is the router which has the most hop away from router 6. That's why router 6, we can check this one. We show forwarding table, we can see for going to router 1, router 6 has two ways to go. Can go through this router, I believe it is router 5, and then this router. I think it is router 4. Then if we want to show the details, then can show the details specifically for router 1, for the loopback of router 1. Then you will see it is ECMP. And show IP7. This is for showing the labels that will be used. Here, this time we can see the labels are different because they are using different sRGB ranges. That's why the labels are different. This is for ping, pinging to the link that connecting to the pinging through the link that connecting to R4. It is successful. And then trace route through the link that connecting to R4. It is successful. This one is pinging through the link that connecting to R5, successful. And then tracing through R5, also successful. And then finally, we will do the trace route. We will do the trace route to router 1. Then we can see it is going through the ECMP path. And because it is going through two routers, so we can see actually the labels are not the same for router 4 and router 5 because they are having different sRGBs. Yeah, this is the end of the task 2. Then the next one will be task 3. Task 3, we will do the traffic engineering segment routing panel. This is different from task 1 and 2. Task 1 and 2, we were doing the short test path, which follows the IGP. And then this one, we will mention about the path that we want the router to go through. For example, for router 1, we want it to go to router 6 through this path. Router 1, router 2, router 3, router 4, router 5, router 6. And then we want to reserve the bandwidth of 100K for that. So this will be the configuration. Let me go to router 1 to do the configuration. And by the way, you can refer to this list for all the other routers for the TE path that we want it to go. Let me bring up the topology a bit to visualize it. Let me share again the screen of the topology. So basically on router 1, we want to do a TE path to router 6 through this way. We want to go router 2, router 3, router 4, router 5, router 6. We don't want to go through the short test path directly. Just what we have, no matter we have whatever reason we want to do this, but we just want to do this configuration. So it will be R1, R2, R3, R4, R5, and R6. Let's see how we can achieve this. And we need to log into router 1, and it is router 1 here. We need to go into the configure terminal, and then we need to define an explicit path called SRTE path 1. We define a path, and then this one is the hop by hop address that we want it to go through. For example, it is saying that to go through router 2, router 3, router 4, router 5, and finally arrive to router 6. We need to define the path option here. So we just apply this configuration. Then now in our path, there are 5 hops that we specify. It will go through router 2, 3, 4, 5, 6, like that. Finally, the destination is 6. And then we need to create a traffic engineering tunnel. In Cisco is configuring like this tunnel, and we can configure the destination is router 6, and it is an MPLS traffic engineering tunnel with a bandwidth of 100, and then with the path option that we defined just now. I mentioned it is segment routing. And create a loopback for testing the tunnel. We will create this loopback on router 6 for testing the tunnel as well. This 192.168.6.6. So basically, we are doing a traffic engineering tunnel to let router 1 use for reaching 192.168.6.6. You can just imagine this 192.168 something is the customer traffic. And then in order to build the traffic engineering tunnel, we need to do some configuration under the interface to enable traffic engineering under the interface that connecting to other routers. And that's it. Maybe when router 1 is separating the configuration like this, it is a bit difficult to see the whole configuration. Now this is clearer. For router 2, you can see the configuration is basically like this. We will create a path, and then we will create a tunnel that using this path, and then we will create a loopback for testing this tunnel. And then on all the interface that we are running IGP, we will enable traffic engineering. Actually, this command, MPLS traffic engineering tunnel command, is enabling the OSPF to advertise additional information for traffic engineering purpose. It is the extension that we mentioned earlier in our presentation. Then we can enable this using MPLS traffic engineering tunnels command. No, it is unidirectional. Yes, you have to configure, yeah, another traffic engineering tunnel on router 6. Traffic engineering tunnels are unidirectional. So now let me apply the configuration to other routers, because actually in this lab also including like router 2, 3, 4, 5, 6. Basically, we need to do TE tunnel on every router, and then we will need to test them. And the TE path is the longest possible path. It is just for demonstrating. Okay, so let me go to router 2 and quickly apply the configuration. Actually, some of you may realize that the configuration is not very different from RSVP-TE signal traffic engineering tunnel, at least from the syntax point of view. I mean, in Cisco IOS, the configuration is very similar to RSVP-TE signal tunnel, but the difference is with segment routing, the intermediate nodes, the router along the way will not need to keep track of the status of this tunnel. Only the head-end router will impose the label. Basically, the path is encoded on the header of the packet, not tracked by the intermediate routers. So now let me apply the configuration on router 2. I will go through each of them quickly, because basically they are doing the same thing. They are doing the configuration we are doing the configuration on each router for creating a path. This is the longest possible path to a certain destination. And then we create a tunnel, and then we create a loopback for testing this tunnel, and then we enable traffic engineering capability in order to establish the tunnel. So each router will be the same. I will just go through each of them quickly. This is router 4, then router 4. We will apply the same configuration. You can see here router 4 is making a tunnel to router 2. I think it is because of originally in the topology, router 4 and router 2, they have a direct point-to-point link. That's why in this lab it's trying to say that, hey, don't go through the direct point-to-point link. Router 4, you go through 6, 5, 3, 1, 2, then finally arrive to router 2. Then for router 5, router 5 also we use the longest possible path to arrive to router 6 for demonstrating the traffic engineering. And router 6, I believe the same. We use the longest possible path to arrive back to router 1. And just let me paste the configuration. So this one shows clearly about the previous question, whether the TE tunnel is one way or two way. It is one way. It is unidirectional. It is only for going. For returning back, we need to configure another tunnel at the destination node. And for verification, we can verify now by using the command. Now I will start from router 1, show MPLS traffic engineering tunnel 0. Now the tunnel is up, the operational state is up, and then it is saying that the tunnel will go through this one, this one, this one, this one, and arrive to this one using these labels. Then if we show IP route, I believe in here show IP route, the purpose is we want to see the 192.168.6.6. Yeah, because router 6 created a loopback 192.168.6.6 for testing. And then from router 1, we created a static route for pointing this loopback to go through the traffic engineering tunnel. Basically, we just want to test whether our traffic engineering tunnel is working. Let's ping and see. Yeah, ping is working. So we need to do the trace route. Okay, when we do the trace route, we see it is going hop by hop and it is working. Same for router 2, we will go through the same verification process, showing that the tunnel is up. Then next, we will show IP route. And then for router 2, based on the lab instruction, the destination that we will test is 1.1. Yeah, because basically we will use the destination that originally it should be the neighboring router, but we try to make the longest possible path to go to it. That's why router 2 is testing to router 1. And then if we ping, yeah, it's working. And we trace, you can see router 2 to router 1, actually they should be directly connected. So it should arrive within one hop. But the reason why it is going through 1, 2, 3, 4, 5 hop, because it is the traffic engineer path. Sure, in real world implementation, you will not really create a TE path just for pinging between your loopbacks. Definitely, you will direct the customer traffic onto it. Now, router 3, we will do the same verification command. We see the tunnel is up and the labels are as listed here. And then we need to do the show IP route. Let's see what is the destination that we need to test. It is 5.5. I believe because router 3 is directly connected to router 5. That's why we are testing this destination just to see whether it is going through the longest possible path that we have defined in the traffic engineering. Yes, it is not going directly to router 5. It is going through many routers before arriving to router 5. And then we will test on router 4. Basically, it is the same test. We will see whether the tunnel is up, and then this will be the path. Basically, I believe our destination will be router 2. Yes, here it mentions about 2.2. So router 4, we will do a test to 192.168.2.2. And we will go through router 6, 5, 3, 1, and arrive to router 2. Let's show IP route and see whether 2.2 is through tunnel 0. Yes, it is. And then we can do the ping. The ping is successful. Then we do the trace. And we can see it is going through the router hop by hop. Next for router 5. Router 5 also we will do the same verification. The tunnel is up. The destination of the tunnel is 6 because 5 is next to 6. And then I believe the destination that we need to test will be 6.6. Yes, it is through tunnel 0. And then we can ping. Works. Trace. It works. Okay. Then the last one would be router 6. Router 6, as I mentioned, it is building a tunnel to router 1, back to router 1, because the tunnels are unidirectional. So yes, it is going to router 1, and then it is going to 4, 5, 2, 3, 1. And if we show IP route, we will see 1.1 is routing through the TE tunnel because we just configure it using the static route to let it use the TE tunnel. And ping is working. Then trace. Yes, it's working. So that's it. This is the result that we want. Basically, we are trying to use the traffic engineering tunnel to direct the traffic through other paths to the destination that is supposed to be next to our router. For example, like from router 2 to which router just now? For example, from router 2 to router 1. Router 2 is supposed to be next to router 1. They are directly connected. So without the TE, actually router 2 to router 1 should be only one hop. The trace route will not show so many hops like that. If we go back to the router 2's trace route, the trace route should not show so many hops. The reason why that it shows so many hops because it is routing through the TE tunnel. That's why it is showing so many hops. Okay, so that's it for the live demo for this lab. Do you have any question about the lab? Real life example, for example, can you give some context about it?
In real life, why we use this? Because
Yeah.
if one router is next to each other, why I need the traffic engineer?
Yes. Actually, in this lab, the reason why we are doing between the two routers that are next to each other because we just want to show that TE is working. But talking about the application of TE in real life would be maybe you have a service provider network and most of the time your traffic will be going through the shortest path that is calculated by the IGP. But there may be some certain requirements. For example, the shortest path might not be the lowest latency path, or maybe the shortest path might not have enough bandwidth to support a specific application. Let's say currently your shortest path is used by most of the customers, and it is almost 80 or 90% full. But now you get a new request from a new customer saying that I need huge amount of bandwidth from point A to point B, and I need it immediately. So for you, you can use traffic engineering to direct the traffic of this customer through a specific path that you define, which is not the shortest path. This can be an application for the traffic engineering. Yeah. Or in some cases, it can be low latency path, because sometimes the direct path might not be the lowest latency path also. Although it may be direct in terms of routing. I mean, when you ping, it is point to point, it is directly reachable. But maybe the submarine cable is routing through a longer distance. So in that case, it might not be the shortest, the lowest latency path. Then you might want to direct certain traffic through the low latency path. Then in that case, you will calculate through which router will be the lowest latency, and then you will impose this PE policy to steer the traffic to that specific path.
Don't we have this function in IGP by manipulating the metric?
Yes, you can manipulate the metric, but that one will apply to all customers. And the reason why we need traffic engineering, because we don't want to apply everything the same to all the customers. We want to have differentiated services. For example, maybe your regular internet users, they might not care so much about the latency, but you have an enterprise customer that will run the voice over IP. So in that case, they will need a low latency path. So you want to optimize specifically only for this customer who will pay you extra money for that. You don't want to use the best link for all the customers, because sometimes the best links can be expensive. Any more questions? When you finish the lab, you can click yes and my lab, then you can close the window. Because in the APNIC Academy platform, you can launch only one lab at a time. So if you are running one lab, you cannot open another lab. That's why it is important to end one lab before you go to another lab. So all good. If there is no more question, then I would like to say thank you very much for participating in all 4 sessions of the segment routing. Thank you. And if you don't mind, maybe we can have a group photo together. Yeah. Also, after the training, don't forget, please help us to fill in the survey form. Yeah. If you certify our training, also let us know. If you don't certify, also let us know how we can improve. Thank you very much. Let's take the group photo.